In this section, we will be talking about position, velocity, and acceleration. The first function that we need to discuss will be the position function. You can think of the position function as your original f of x. In all of the information we've been talking about, we realize that we have our original function. Then we would have something that later on that we'll talk about, that is the velocity function, and that's going to be the derivative of your position function. So when we talk about how objects are moving, then a horizontal movement, left to right, that would be something like people, just everyday cars, and even a river. That has your horizontal motion, whereas your vertical motion, then that's going to be something like a rocket. You could have really anything subject to gravity. Anything that is subject to gravity. All right, so that's looking at the different motions or positions that we might have. Now, whenever we talk about the derivative of the position, we get velocity. And so whenever we talk about that, we had a couple of different rates that we looked at. The first rate that we talked about at the very beginning of the school year was an average rate of change. And so this is what we talked about when we had just our slope formula. And then we talked about an instantaneous rate of change at a precise moment in time, and that's going to give us our velocity function. Now, when we start talking about all these different functions, all of them have specific things that they do. So for the first one, if we're going to talk about how our motion is going with our velocity, we have to keep in mind a direction here. So with our velocity on a horizontal line, if our velocity is positive, then we are either moving right or we are moving up, whereas if velocity is negative, we would be moving left or we're moving downward. And if velocity is zero, then that tells us in both times that the particle is stopped. Okay, moving on. We next talk about speed, and we do need to note that speed is the absolute value of velocity. And then we can move on now to acceleration, which is the rate of change of the rate of change, or it's the rate of change of your velocity. So to summarize all of this, we actually have three different functions that we will be talking about. And the first function that we have was our position function, and then we have our velocity function, and then we have our acceleration function. As we move down this chain, we are actually finding the derivative of each one. As we move up, we will be finding what's known as the antiderivative, and that's what's coming up pretty soon. Okay, and then finally we talk about acceleration, and acceleration is doing the pushing. So if our acceleration is positive, then our particle is being either pushed to the right or is being pushed up. If acceleration is negative, the particle is being pushed left or it is being pushed downward. And then finally, if acceleration is zero, that means that our velocity is constant. It's not changing. Okay, now when we talk about an object speeding up or slowing down, then we look at the signs. If velocity and acceleration carry the same exact sign, so they're either both positive or both negative, our object is speeding up. If velocity and acceleration have opposite signs, then the object is slowing down, and you can think of it as they're working against each other. So the particle would be slowing down quite a bit. Okay, now let's look at our graph. And our graph to the right here, notice that this is the graph of velocity. Always take note which function that you've been given. So the first function that we have is our velocity. And also our x-axis is going to be in terms of time. So the first question they ask us is, when is the particle moving at a constant speed? So if we're moving at a constant speed, that means that my acceleration is going to be 0 because we're looking at a derivative. And notice if you're looking at your graph here with your velocity, notice that for this area here from 0 to 1, we're moving at a constant speed. So the answer for number 1 is going to be from 0 to 1. Okay, now we're looking at when is the particle moving to the right. So if my particle is moving to the right, then I know that my velocity is positive. So we have to look over which interval is my velocity positive. And when we do that, notice that we're going to have from here to here, and we're also from here to here. All of that's above the x-axis, so everything here is positive. So that tells me from 0 to 2 is going to be whenever our particle moves to the right. When is it moving to the left? Well, let's look and see. If we're moving to the left, that tells me that happens when our velocity is less than 0. So that's going to be all of this below the x-axis. So we're going from 2 to 5. Okay, now the next part, and I'm going to erase all that I put on this graph because next they're talking about speeding up. And we were just looking at speed is going to be the absolute value of velocity. So if speed's the absolute value of velocity, we can make a speed graph. So now I'm going to change this to a speed graph, and I'm going to flip all of this that's negative, I'm going to flip it over and make it positive. So really this negative portion becomes positive, and so this whole portion here, once I flip that over, this becomes the graph of speed. So if that's the graph of speed, I need to know when is the particle speeding up or when is this increasing. So this function is increasing over the interval from 2 to 3. Right through here is where that speed is increasing. So my answer for this next one is going to be from 2 to 3. Okay, so for this next problem, number 5, we're asked when is the speed slowing down? So to find out when we're slowing down, again, let's make this graph into a speed graph. And so that's where we had to flip over. And so let's see what's going on with that. So if we are slowing down, that means that the speed is decreasing. So it looks like our speed would be decreasing from 1 to 2. And it also looks like from 3 to 5. So here we have two intervals. We have from 1 to 2, and we also have from 3 to 5. Okay, and now we're back to velocity, so we need to erase all of this that we had, or you don't have to, but I will just to keep all of this straight. And now we need to know when is velocity increasing. So whenever velocity is increasing, so that means our acceleration would be positive. Now, just because this says increasing, that does not mean that the function itself is positive. The function can be negative here. So v at t can be, and we need to write this in, negative and increasing. That is possible. And it's possible from here, from 3 to 5. It is very possible over that interval from 3 to 5. So here, to find out where velocity is increasing, so looking at our graph, and if you wanted to talk about acceleration here, because if velocity increasing, that tells me that acceleration is positive. So in other words, the acceleration, we can think of that as the slopes. Those slopes are all positive. So if I go in and I try to sketch a tangent line somewhere along here, notice all of those lines have a positive slope. So here is going to be from 3 to 5. All right, so our next question, where is velocity decreasing? And so just like earlier, you can have a portion of your velocity graph decreasing and to be positive. You can also be decreasing and negative. So looking at this graph, I see that my velocity is decreasing from 1 to 2, and it also looks like from 2 to 3. We are also decreasing. So here, and there's a small break here, so we do need to be careful with that. So we're going to say that our velocity is decreasing from 1 to 2, and also from 2 to 3. Oh, well, it'd help if I put that T in between there. Okay, now number 8, it wants to know, are your answers to questions 6 and 7 the same as 4 and 5 respectively, my goodness, sorry, and you need to explain. So are those two the same? So looking back at questions 4 and 5, you were talking about speed, and then over here in 6 and 7, you were talking about the velocity increasing and decreasing. So here, let's see, are they the same? No, they are not the same. The reason why they're not the same is because velocity increases, so v at t is increasing where a at t is positive. And that's not always the case with speed. Remember, if you're speeding up, that means either both signs are positive or both negative. So here, that's a little bit different. Okay, our next question, number 9, is asking us how fast is the particle moving at time t equals 4 and in what direction? So notice it's talking about how fast the particle is moving. So that's really talking about your speed. So if we want to know how fast we're going at time equals 4, to find speed at 4, we need the absolute value of the velocity at 4. Okay, so let's go over here. Let's find our point at 4. It looks like we're over here at -5. So this is going to be the absolute value of -5, which is going to give us +5. So there's how fast we're going. Now the direction that we're going, notice velocity was negative, so we are moving negatively, or we're moving to the left. Okay, and the next question asks us, well, what is the velocity, the particle's velocity at time t equals 4? So the velocity, or v at 4, is -5. Velocity can be negative. Speed, however, cannot be. Okay, so our next question, number 11, wants to know, what is our average velocity over this time frame? So if we're looking for average velocity from 2 to 3. Now, those of you that have been in physics will understand a little bit better how to find this. If you're looking for average velocity, you're not looking for an instantaneous velocity. That's going to be what's going on at that precise moment. So this is going to be a little bit different. If you're looking for the average velocity, really the average velocity, AROC, of V at t, can be approximated by finding the position. So we're going to say the position function, s at 3 minus s at 2, and that's all over 3 minus 2. So that's going to be your average rate of change. Now, we don't have any function that we can look at, and this is why from physics, a lot of times if you were asked for that average velocity, then you're looking at what's going on under the curve. And this is why you were told in physics, you're just going to find the area bounded from 2 to 3. So let me show you what that means. We're going to go up here from 2 to 3, and we're just going to kind of section off this portion of the graph. So to find this average velocity, then what we're really going to do is just find that bounded area. We're finding what is the area of this region here. So in order to do that, we need to recognize that this does make a triangle, which I'm pretty confident you all do. So here inside this portion, we just need to find the area of this triangle here, and then we've got it. So the area of that triangle, well, our area formula is going to be 1/2 base times height. And so let's see, we have 1/2. Our base, well, the length of that base is 1. And our height is going to be all the way down here, which looks like it's over at 10. Now, don't include the negative just yet. We'll talk about that here in just a minute. So just trust me for this one. So you've got 1/2, 1 times 10, which is going to give us 5. Now, since this bounded area is below the x-axis, we're going to make it negative. Now, I understand if I used -10 earlier, then it would have been negative, but we have to be careful with this. We could have done something completely different with this in a different situation, following that same thought process, and you're going to miss your sign. So if you'll just assume all of it's positive, and then once you look at your final region, if it's below the x-axis, just make it negative. So here, my average rate of change of velocity is going to be -5. Okay, so for our next problem, we're asking, when does the particle change directions? So again, looking for when that particle changes the direction it's going. That's going to help us here, because if we're changing directions, most of the time you're looking for the x-intercept. And that's because you need to know where is that velocity equal to 0, because that's where the particle stopped. And once that particle stops, a lot of times it's going to change direction. So my particle is stopped right here at x equals 2. Or, well, let's say that's really our time equals 2. Okay, and this next question is a good physics question as well. And this is saying, looking at this graph, how far does the particle travel or move during the first second, and which way? So keep in mind that our time is going to be our x-axis here. And so to find out how far we've moved in that first second, it's just like finding that average rate of change of the velocity, the AROC of the velocity. This is the same thing. So we just need to find the area of that bounded region again, because this is really talking about position, but I'm given the velocity. So I need to find the bounded area. Okay, so again, underneath here, we see that we should have some kind of rectangle We see this side length here is 1. This side length up here is 5. And so 1 times 5 is 5. So the position of the particle is going to be 5 units. And which direction? Let's see. We were not given it. We're just going to say units. This didn't write the first time. Units per, we wasn't given that other either. So we're just going to say per time, or whatever the heck it is. Now, which way did this move? We're above the x-axis, so we're positive. So it's going to move to the right. And it's moving to the right because via t is positive. Okay, now let's look at number 14. Number 14 asks us, how far right does the particle go when does it arrive there? So, well, we already know that the particle is traveling to the right 5 units after 1 second. And so notice that our particle continues moving to the right until it gets to 2. That's where we said the particle changes direction. So we now need this bounded area. So that's going to be the area of a triangle. So we have 1/2 our base, which is 1, times our height, which is 5. So that area is going to be 5/2, or what is that, 2.5. So I know that I've traveled 5 units after 1 second. And then after another second, I've traveled another 2.5 or 5/2. And so my total distance all the way to the right should be 7.5 units. And it asks, when does it arrive there? It arrives there at time equals 2. Number 15, we're wanting to know what is the total distance traveled by the particle. So we're going all the way over here to time 5. Again, we're talking about a distance, so we need to look at the bounded area again because we're given velocity. Total distance traveled by the particle. We know once that particle reaches here, it was traveling at 7.5. So now we need to find this bounded area here. Now we have to keep in mind that total distance is positive. This is not talking about displacement. This is talking about distance. So when we find this region under the x-axis, we're going to keep that positive because even though the particle's really traveling back to the left, it is going a particular distance. So let's go ahead. This is another triangle, so we're going to have 1/2. The base is 3 units, and the height, it looks like that's going to be 10 units. So that distance there is 15. I know that it's negative 15 because it's under the x-axis, but that would be its displacement is what's negative. Displacement is going to give us negative 15, but the actual distance is positive 15. So our total amount of distance is going to be 7.5 plus 15. So that's going to give us 22.5. That's the total distance traveled. Now, the next question asks us, what is the particle's position after 5 seconds? Now this position here, that's a little bit different. So that's going to include our displacement because the position can take into account for the negative. So after 2 seconds, the particle has traveled 7.5 units, but it's going to turn around at 2, that particle is, and it's going to travel back to the left 15 units. So at the what is the particle's position after 5 seconds? Well, that's going to be, so notice that we're at 7.5. We've turned around and gone back 15. So really, we want to say, well, we're at negative 7.5. So a good way to state that would be 7.5 units. And which direction? That's going to take care of that negative. So it's going to be 7.5 units to the left. Okay, moving on. Number 17 wants to know what is the average velocity of the particle over the 5-second time interval. So average velocity, again, that's talking about an AROC. We were talking about the difference in the positions. So we just got finished looking at displacement. So it's really going to be displacement over your time. So let's look at this and see if we can figure out our displacement. We had 7.5 minus the 15 units back to the left over our time interval, which was 5. So 7.5 minus 15, that's going to give us sorry. And so that's going to reduce down to be negative 1.5. Okay, so now number 18. Are your answers to questions 15 and 16 the same? And so, no, they're not the same. Definitely not. And the reason why is number 15 is talking about a total distance, whereas number 16 is talking about displacement. Right, our next question is asking us for the average speed. Now remember, average speed, that's talking about where we have positive, remember we have the absolute value of the velocity. So really we're talking about here, we're getting rid of the negatives. So speed, we're talking about our distance divided by our time. So that's going to be a little different. Our total distance, well, we had to make that was a positive here. And then over here we had positive. So our total distance was 22.5. And that's going to be divided by our time interval, which was 5. And so that's going to give us 4.5. That's going to be our average speed. Now number 20, what is the particle's acceleration over the first second? And what does your answer mean? So this is kind of redundant. We looked at this in the very first question. So over the first second, so we're looking at, again, from here to here. And now we want to know what is acceleration. Now when we talk about acceleration, remember that is the derivative of velocity, or we're talking about the first derivative. If we've got our velocity function, then we're talking about that first derivative. So here, the particle's acceleration, well, this is a horizontal line, so I know that v prime here, just like f prime, that's going to give me a 0 there. Because it's a constant, it's not going to have a rate of change. So here, a at t is over that first interval, or that first second, is going to be 0. And it's because, oh, well, it didn't ask why. It asks us, what does our answer mean? Well, that means that v at t is constant. Okay, moving on. For our next question, over what time intervals does the particle have positive acceleration? So positive acceleration, that's going to be where our velocity function is increasing. So positive acceleration, that means v at t is increasing. Just like if we had a positive first derivative, then our original function was increasing. Same process here. So if my velocity function is increasing, which is going to be from 3 to 5, all of those slopes will also be positive. So my answer is going to be from 3 to 5. Number 22, over what time intervals does it have a negative acceleration? So a negative acceleration, that's going to talk about where v at t is decreasing. So hopefully we're seeing the similarities there. And so here we are decreasing from 1 to 2, and we are also decreasing from 2 to 3. And please don't put those together. There is a break there. We're hitting a 0 here, so make sure you note that. Number 23, when is the acceleration? Undefined from 0 to 5. So if you're looking for where we're undefined, now acceleration, talking about that being undefined, that is the derivative. That's talking about where is v prime undefined, and v prime is going to be undefined at sharp turns or discontinuities. But here we are continuous, so we're looking for those sharp edges. Where would we not be defined? So it looks like we have a sharp edge here at 1, and we also have another sharp edge at 3. So here, where is acceleration undefined? It's going to be undefined when t equals 1 and when t equals 3. Okay, number 24, state the interval of time when the particle has a positive acceleration but is slowing down. So a positive acceleration, that's going to tell me that v at t is increasing but slowing down. So here, slowing down, that means that v at t and a at t have different signs. So we already know what we want v at t to have. A at t we want to be positive. So we need to see then, this is a strange question, we need to see where v at t is increasing, and where is v at t negative, which implies below the x-axis. Well, where is v at t both increasing and below the x-axis? Well, that's going to be from here to here. It's going to be that time frame there. It's going to be from 3 to 5. Okay, next question. Number 25, state the interval in which the acceleration is negative. So I'm going to stop there. Acceleration is negative. Well, then that tells me that velocity is decreasing, but the particle is speeding up. So that means velocity and acceleration are working together. So I know where velocity is decreasing, but I also need to know where velocity is negative. So where are we negative and also decreasing? And that very quickly we can see that's going to be from 2 to 3. Okay, and then number 26, what is the particle's acceleration over the time interval from 3 to 4? So we want to know what is the particle's acceleration, but all we have on this interval from 3 to 4, all we're given for that is velocity. So let's go back to this PVA business. So for PVA, position, velocity, acceleration, we have acceleration, or no, we have velocity, and we want to get to acceleration. So we need a derivative here, which means that we need a slope. So we're just finding the slope of this line. So let's look at our points. We have at 3, and then we have at 4. Well, that was sweet of them because we have y values for those two. That's awful generous. So I know at 3, I am at negative 10. And then when I'm at 4, I'm at negative 5. And now I need to do my slope formula. And remember, slope formula is changing y's. So negative 5 minus a negative 10 is positive 5 over 4 minus 3, which is 1. So the particle's acceleration over this time interval from 3 to 4 is 5. Okay, the final two, number 27, what is the particle's average acceleration over the entire 5 seconds? So if we're wanting to know the average acceleration, then to estimate that, that's going to be, notice it says average, this is going to be a rock. So average rate of change over the entire 5 seconds, well, we're going to have to go through and look at our V at 5, that's the end, minus the beginning, over the entire time frame, which is going to be 5. So knowing that, we know that at V at 5 is 0, minus, and I know V at 0 is 5, and that's going to all be over 5. So the average acceleration over the entire 5 seconds is -1. And number 28, over what time interval is the particle's velocity decreasing at a rate of 5 feet every second? So at a rate of 5 feet every second. So let's look up at the graph. Velocity's got to be decreasing. And so it looks like for 5 feet for every second, so from here to here, so we drop from 5 to 0, so from 1 to 2, that should be our time interval.